Müssen wir gleich einmal. Yeah. All right. Well, thank you for having me. First of all, I'm very happy to be here and also happy that all of you turned out tonight, even though it's very cold outside. I'm going to talk about something that is very much back to the basics. I'm going to talk about intent-driven API design in C++ and choosing parameter types without memorizing rules. Because we've all learned, or I hope all of you have learned C++ at some point. And we know that there's so many rules in C++ that you can learn in order to make the right choices when designing APIs, choosing the right types. There's so many mechanisms. There's so many things in the standard library that we can memorize. But often that doesn't really help because we don't always read 1,000 kilometers of rules before we make a choice. We want to make choices like pretty quickly. So why am I talking about this? Because, well, I've been down this road. I also learned C++. After first really struggling to make a compiler work for some time, I had a course at university. I learned C++. And, well, even after working with it for a couple of years, I still often found myself guessing, what parameter type should I use for this API? Should I use a const reference or should I use, whatever? So we learn mechanics or mechanisms. You see something like this. You have multiple signatures. What do they mean? Which one should I use? We've heard about pass by value, pass by reference. Things like this. We have a type that contains some big objects and we pass it by value. Does that make you nervous? What about moving? There's something called move semantics in C++11. We move something and then we use it afterwards. Is that legal? What happens when we do that? What about something like this? We have raw pointers. Raw pointers are evil. We all know that. What happens? I delete this here. Is it a double free? Is it a memory leak? Who knows? So I think the problem is not missing rules. I think the problem is missing first principles. And since I am at 42 tonight, I'm curious, first of all, who in this room has learned C++? I think that's mostly all of us, yes. But then who of you, when they learned it for the first time, learned a pre-C++ 11 version of C++? That's also almost everyone. Well, then who has learned it after C++ came out, 11 came out, and learned also the rules of C++ 11? That's not so many people. And this is kind of, it's interesting because, as you know, C++ 11 is considered the modern C++. And since then, there's been a lot of developments as well, but still, the most fundamental thing in C++ 11 was move semantics. And I remember when I first heard about move semantics, I had no idea what it meant. And even after years of trying it out, I still didn't fully understand it. So that's also kind of the reason why I'm giving this talk, is to make a mental model for how to decide. First of all, I want to talk about a few concepts that are going to be very fundamental to understanding all of this talk. First, I'm going to talk about the concept of a caller and a callee. So what is a callee? It's just an API, basically. It's a function signature. So we have something like this. We have a print function, and we have some sort of parameter type. This would be the API. Or in this case, I also have a bit of an implementation here, but basically the receive and the print, that's my API of whatever code I'm designing. And the caller would be the call site, so where I call this API. So here, for example, I instantiate a message with the receive function, and I print it. It's pretty standard stuff, nothing too fancy. Also, I want to clarify that I'm mostly talking about application programming. Even though I work in the embedded world, I still very much am like an applications programmer. If you are, for example, a game developer, then a lot of this stuff will probably not apply, in the sense that you make very different choices, very different trade-offs. So this is just a general case of, let's say, bread and butter API design. I'm also going to switch over to this side so these people, I can look a little bit at my colleague over there as well. So first of all, lifetime. One of the big concepts which simply answers the question, where is an object created and where does it get destroyed? So let's say a nice metaphor is always a car, for example. It gets produced in some factory, then someone will own it, someone will drive it, and after it's done all its job and it's kind of, nobody wants to own it anymore, it gets destroyed. So here we have a simple scope. Here the scope opens, we create a string, we maybe call something on this object, and then at the end of the scope, it gets destroyed. Pretty straightforward. Here we have just some sort of API that takes an argument. But here we have this special case that we have a reference type. So what does that say about the lifetime of this object? Well, it says that the object that I pass in has to live longer than the scope of this function. So this S will not be destroyed at the end of the scope because it has to live before the call and it has to live after the call. Pretty simple. Now, we also have something that comes with lifetime in C++, which is a risk. So here we have, for example, a type message with a reference as a member. And we take a reference in the constructor of this class and we store it. So this is quite dangerous because now if we use it, for example, we make a new message object, we pass in this std string hola, it will run the destructor at the end of the scope. And we suddenly have a dangling reference because we return this object that we created. It has a reference to something that already was destroyed. So lifetime considerations in C++ are one of the most fundamental things to understand. And also the source of many, many bugs. I can't tell you how many hours and days and probably weeks by now I have wasted on lifetime considerations in multi-threaded environments. So that leads me to ownership. Ownership is kind of a derivative of lifetime and one of the most fundamental things to understand. Ownership is just answering the question, who is responsible for ending this object's life? So before I talked about lifetime, I talked about this car kind of metaphor. So if we talk about ownership, then I can buy the car, I own it, I can use it, I can modify it, I can also give it to someone else to own. And well, who decides in the end when it's time to destroy that car? That is the question of ownership. So here I chose to show some example of like a pre-C++ kind of struct. We have something here called a task, and we have a raw pointer because, pre-C++ 11, we didn't really have that much more to use. Here we have some sort of constructor and a destructor, and I also made the copy constructor private. So basically we cannot copy this struct. Just for the sake of this presentation, to make it easy on ourselves. And the constructor is very straightforward. It creates this impl, whatever that is, might be some sort of callable, doesn't really matter for this example. And we have a destructor which deletes this. So this is very much encapsulated ownership. We own whatever this impl points to, because we create it, we destroy it. So we are the owner of this. Very clear ownership example in this case. So why am I talking about this? Well, what happens when we use this? So here we have something that creates a task. So we have a function that returns a pointer of a task. And then, for example, we can enqueue it into some maybe job processing queue. Then somewhere else we can dequeue that task, and then we want to execute it. That's a very typical thing that we want to do in all sorts of programs. And then here we see, let's say this is the call site again, where we use part of the API. So we create a task here, and we enqueue it. And then maybe somewhere else on a different part of the program, different time, we will dequeue this task, and we will execute it, and then we delete it. Well, what happens when we delete this? Well, the thing is, we don't really know, because it depends on how this type is implemented, and also how this function decides to use or pass the pointer. It will probably have some sort of new call, but who tells me that the execute function, for example, doesn't delete whatever I give it? I don't know. I cannot know. So here we have a problem, because yes, we can make assumptions. We might have conventions, but we cannot really guarantee that this will not cause a problem. We just don't know. Anything in this chain might have already deleted the task. All right, so the solution is very simple, right? We have C++11, problem solved. We use shared pointer everywhere. It's easy, it's reference counted. So whenever we use a shared pointer, we increase some sort of usage count. And then whenever nobody uses it anymore, it gets destroyed. The world is very simple, shared pointer. Well, let's talk about this later. So the other big concept that is interesting is mutability. And it answers the question, who is allowed to change the object's state? So again, the car metaphor might be, I borrow my car to a friend, and I tell them, you're allowed to drive it, but please don't change the color of it, for example. But I might also be cool with that. Maybe I borrow it to a friend who I know does super cool designs on the side of cars, or does like decals or something. So maybe I want them to change it, or I allow them to change it. So yeah, there's the question of mutability. Here we have an example for a mutable API. So this API takes a reference, and it just adds like an exclamation point to the string here, for example. So I borrow this string, but I also say you are allowed to change this. And immutable, on the other hand, is the case where I don't allow it to be changed, so I can only observe. I can use it, but I cannot modify it. Now, in the title of the talk, I talked about intent-based design. So what do I mean by intent? Well, this is kind of the question of, what does my API mean to do with this argument that I pass it? Because again, what I showed up until now were a couple of concepts and some mechanics, but I always have to ask the question, what do I express when I write an API, when I design an API? What do I express to someone who wants to use my API? And this is the question that I try to answer. So in order for this to be the simplest possible, I came up with this model. That is, whenever I design an API, I ask myself these questions. First of all, do I want to own the object that I receive? If so, it's very simple. I am talking about an owning intent. If I don't want to own it, well, okay, so I'm just gonna like borrow it, but I want to know, do I need to mutate it? Do I want to mutate it? If so, I have a mutating intent, and if not, I have an observing intent. Super simple stuff. And this is exactly the core of the model that I developed for myself and that I am now sharing with you. Because over years and years, I always had kind of like the building blocks of this, or like thinking about, okay, how exactly should I design this API? But really making it clear that it boils down to these simple questions for me was like a very powerful thing. And then I came to this realization for myself, for this mental model to really click. I see a function call as a negotiation. So now you might think, what does he mean with a negotiation? Well, I see it like this. An API requests rights. So what I just showed was I want to either own or I want to mutate this object, whatever I ask for. This is the rights that I request from my caller. This is what I want. At the call side, I provide evidence in the sense that whatever I do end up handing to this API will then be notarized by the compiler. So he checks, okay, the API wants this. The caller is ready or is willing to give this type of thing. So it provides a certain type of evidence. And if these two match, then it says, you're good to go. I'm going to compile this for you. If not, you get errors. And yeah, we all know C++ error messages are quite fun to decompose. So let's say here, for example, I just have a simple function that takes a mutable reference. And here I have a const a, whatever that is, and I call this function. Well, the compiler will look at it and say, nope, that does not work because the API asked for a mutable thing, and you are not providing a mutable thing. You are providing a constant thing, so no, that's not good. And of course, if we have the proper API rights matching to what the caller is ready to give, well, then we get a compiling program. Very nice. So let's talk a bit about how do these rights, how does the shape of them look like? How do we express this stuff? And I want to talk about canonical shape, meaning that this is the default that you can think about. Whenever you think about an intent, such as observing, there's a default shape that this right takes. So here, the canonical shape is just a constant reference, very simple stuff. When we mutate, we take a regular reference. If we want to own it, what do we take? We just take t. We just take a value. Now, for me, when I learned move semantics, I thought, well, we'd have to take a double ampersand, double ref here, of course, if I want to move. But bear with me. So now, when we talked about the shape of rights, we also, of course, have to talk about the shape of evidence, like the other side of the equation. So what am I expressing on the call side to the compiler, what I'm willing to give? So here, for example, I have a value, it's not const, and I pass it into this function. What I express by that is, I still need this. This is still needed. You can maybe mutate it, or you can observe it, or you can make a copy of it, but I still need this very much. So the expression translates to an intent on the call side as well, just as the rights on the API side. In this case, I say, I created this, but I no longer need it. So I call move. So my intent is no longer needed. You can do with it whatever you want. And in this case, when we have a function that creates a string for us and we directly pass it into a function, well, basically what it says is, I never needed this to begin with. I just created it for you. You can have it. I don't even care. And if you've ever learned about value categories, well, this is all it is. We could do a long quiz about what type of value category is this and so on, but it's actually quite simple. We just map our intent. We say, if it's still needed, it's an L value. If we no longer need it, it's an X value. If we just created it in the moment and don't even care about it, it's a PR value. That's all there is to it. I mean, as long as you're not a compiler developer, then there's a lot more to this. So then, as I said, we have both sides, or we have the API side and we have the evidence side. And now, when we match these two, how does this work? So here we have three different APIs. We have an owning API, we have the observing API, as I said, with the canonical shape of a constref, and we have a mutating API. And this is, again, this is something that I express. This is my intent that I express. Now we have a couple of objects here, a couple of strings. Just to make it clear, we chose three different ones, and we also have a function that creates a string for us. Now let's start matching this. So if I call the owning API, well, this is fine, right? Like this makes a copy. It's great. The function body of this owning API, it will have a full-on object. It can do whatever it wants with it. It can mutate it. It can put it somewhere else. It can store it. It doesn't matter because it's a copy, and I still own at the call site. I still own whatever I passed in. Very, very simple stuff. Now, what if I say I no longer need this, and I pass it in to this owning API? Well, that's also fine, right? I say you can have it, and in this case, the move constructor will be called of this string object inside the body. And again, from the API side, inside the function body of this function, it will just be an object. It won't even be visible whether we call the move constructor on it or whether we call the copy constructor on it. The simple fact is I have a value. I don't care how it got to me. I just have a value, and that's what I operate on. I own it. It's mine. Now, what happens if we do this? I never needed this intent, kind of. It's also fine, right? Because it's just a temporary. It gets, there's actually some elision and all that kind of stuff, but you can mentally think about move constructors. So we create a value that is temporary. We don't have any sort of reference here on the call side. It just gets move constructed into the type, and we're good. Okay, so in the owning case, it seems like all of these three evidence categories are accepted. Compiler is happy with this. It's going to work. Nice, okay. So what about the observing? So here we have, again, a string, and we pass it into this observing API. And of course, in this case, we just observe it. We just take whatever, maybe we print it. Maybe we will check a certain value for validity. We don't know, whatever it does, but it's fine. The compiler is happy. Now, what if I say I no longer need this, and the API requests the right to observe it? I mean, is that fine? Yes, it's absolutely fine, because there's actually a very interesting fact about C++, and that is that constref binds to everything. Anything you throw at it, basically, it binds to it. So this will extend the lifetime of this object just enough for the function to complete. In the beginning, I showed that lifetime is important when you deal with references. So it will outlive this function, and only then will it be discarded. So this is also fine. Now, I already kind of hinted at this, What if we make it temporary? What if we have the evidence type of, I never needed this? Will it work with the observing? Yes, it will, actually. This is another of these cases where constref just binds to everything. And this temporary will actually also just be alive long enough for this function to do its job. And then, it will go out of scope and be destroyed. Now, what about mutation? With mutation, as I said earlier, it needs to survive the lifetime of this object, whatever we pass in, has to be longer than the duration of the function. So here in this case, it's fine, right? It might be mutated, who knows? Maybe there's going to be another language in it, maybe there's another exclamation mark, we don't know. It just has the right to mutate. What if I move it in? Well, I already hinted at it. It doesn't work. It's not a mutable value. It's not a mutable L value in this case, because we say, I don't need this anymore, but the function says, I want to mutate it, but then what? Like, where is it going to be? How am I going to access this? Doesn't really make sense. What about a temporary? If I pass in a temporary and I want to mutate it, doesn't work, right? Because it's the same thing effectively as before. I mean, I cannot mutate a temporary again. It doesn't really make sense. I don't have any identity. I cannot really access it anymore. Now, I still haven't talked about one thing. I have mentioned it, but let's see. There is actually an edge case here of the owning intent. I presented the T, but let's take a closer look at this owning intent. Because until now, what I showed was that, let me actually go back to this. So here we have this owning API. We say, I want to own this value. And all three cases are fine. All these three value categories, all these three evidence types are fine. In the observe case, also all three are fine. So it's kind of, it seems like it doesn't really matter what kind of evidence or what kind of value category I have here. It will be fine for either one. Okay, but what if there is actually a question that I can ask, and then I can either take, like I can have a call that is legal, that is based on what the call side provides. It was a bit complicated. Let me try a different approach. So for now, it seems like no matter what the evidence is, it's all the same for the compiler. It will just accept it, whether it's owning or whether it's the observing. But what if I want to own only if the caller says, I no longer need this? Only in that case, I want to take the object. So that means I have here, that's what I talked about earlier, the unconditional owning intent. I want this no matter what. I don't care if it's copied, if it's a temporary, or if it's moved. That's this case. But what if I want this to be conditional? I want this only if the caller says, I no longer need it. That's the only thing. Okay, well, I don't know. Maybe some of you already know. Let's take a look. So maybe somebody already knew I was going to show this, the double ref, whatever you want to call it, R value reference. A bit of a weird nomer, but yes. In this case, for example, we have a type here that I don't know, it's like a database connection. And now, here in this case, the compiler will say, no, this cannot work. This API wants to consume this object, which is kind of the same as owning, but with the difference that it says only if the caller actually proves that they do not need it anymore. So this is the only type of intent that I can express where the evidence actually makes a difference in terms of ownership. So here, in this case, the only way to prove to the compiler the right type of evidence is to call stdmove. And then only in that case, I say I no longer need this. This type of API with the R value reference will be a legal combination. The compiler will notarize this contract. The compiler will say, yes, you can do this. And also, if we just create something on the fly right here, well, of course, it's going to be fine as well because I never needed this. So you can have it. It's kind of almost the same as no longer needed. It's just like I actually didn't even need this in the first place. So the question here, I was kind of struggling a little bit to come up with a question to decide whether I want this or not. Do I want just the T? I want to own it at any price. Or do I want an R value reference? The question is, do I want to distinguish between copying or moving? Do I need to actually make a difference between these two? Only then do I really need to think about this type of API. And I argue that in, let's say, 99% of cases, I do not need this. You can argue with me on that later if you want to. But in all these years of designing APIs, I rarely ever use this. I don't know if I've ever come across a case. The only memory that I have of using this was very much in the beginning when I started learning about move semantics. I used this a lot. I was like, oh, this is great. Now it's all cheap, premature optimization everywhere. It's so fast. But ultimately, when I use this more and more, I realize it's actually more of an anti-pattern. Okay, so just to make this a bit clearer as well, like what do I mean exactly by distinguishing copy versus move? Why would I even want to do this? And the one thing I could really come up with, because it's very common in the STL, is something like a vector. If I made a class that was some sort of container, like a vector, then this is the one case where it really makes a lot of sense. And here we have something like a pushback function that either takes a constref. So it's like we say we observe it, but actually we use this as a copy in. So we say in the case of someone calling this with not being willing to give it up, but they still want to own it, then this one will be called, and we can make a copy. Or otherwise, if they say, actually, I don't need this anymore, or I made this just for you, then this one will be called. So here, we have just a small example. Here, this would be the copy in path, and this would be the move in path. Now, why do they even do this? Why don't they just take T? As I said, owning. I just want to own it. Why don't we just take T? Well, because it's a library that is used in so many different applications that they very much care about the performance right here. They want to really squeeze everything out of it, because what if we use this in some sort of hot path where we have a loop that pushes stuff into a vector, takes it out, whatever? This should be the best performance possible in this case. So here it makes sense. But if we had, for example, more of these, let's say we have a container type that always takes two things at once. I don't know, it's a bit contrived maybe, but then suddenly I would have to have one pushback that takes, let's say, a T and a Z, and takes both by R value references. Then we have, that's the first case. Then we have the case where the caller wants to give up one of them, but not the other. Then we need one that is T ampersand ampersand and the constref. And then also maybe the other way around. Maybe it is willing to give up the first one, but not the second one. Then we need another overload. So we already end up with 4 overloads. And now if we have 3 maybe parameters, you get the picture. We get some sort of combinatorial explosion. And this is why a lot of the STL types actually have this, but they often just take one argument, or they do trickery with templates and perfect forwarding, which I consciously decided not to talk about today. But if you guys have questions about that, we can do that. Now, how many people here have heard that std move is not, it doesn't actually move and is a bad name? Okay, quite a few people, yeah. So why is that? Why is std move an unfortunate name? I think most people, usually the answer that I hear is, well, because it's just a static cast. It's not actually moving anything. That is technically true, but it doesn't really help me. Like, it's just another layer of complication. Okay, what does that mean? It's a static cast to an R value reference. Okay, that helped. I don't know. I'm not smarter. So why is it an unfortunate name? Well, it's what I said before. It doesn't actually move anything. Okay, let me take a step back. So here again, we have this consuming API, but note that here I just have an empty body. In the case of the observing API, we say, okay, well, I still need this. This is fine. I move it in. It's also fine. But what if I call the consuming API? It says it's consuming anyways. And I move it in. I say I no longer need this, but I have an empty body. What happens? Yeah, pretty much nothing. So this actually doesn't move anything. I still have this OI parameter here. I still own it. It's still in a valid state. I said I no longer need it, but why is it called move? It shouldn't be called move. It should be called maybe something like, I don't know, give up or relinquish or release or I don't know. But I guess it's too late. Maybe I could give a proposal to the standards committee. I don't know how likely that would be to pass, but I could try if I have a lot of time. Now, in the case of this owning API that I showed with a value type, with just T, or in this case, std string, well, it very much does move, even if, oh, actually, I think I wanted to make an empty body here as well for the own function. So here, very much I would just make a copy, and in this case, I would actually move. So in this case, yes, it does move, because it moves it into this, into the move constructor of this, and it will actually take ownership. And then if the body is empty of the function, it will go out of scope, it will destroy it. Very nice. So just kind of like a detail of why std move is actually an unfortunate name, but this time looking at it from the point of intent, the point of what am I trying to say? Not just the mechanics, but what am I actually trying to express here? And that's why I think it's a bad name. Not because it's a static cast or an R value reference that doesn't really say what I want to do with it. So I very much always think in these terms of like, what am I trying to express? Because code, yes, it's for the compiler, but mostly it's for humans to reason about. So I always want to think about the intent. Why did somebody choose the way they chose it? So here, as I said, I have the still needed type of evidence, an L value, if you want to be technical about it. We do the std move and we forge the evidence, let's say. We say, actually, no, this is an X value. I no longer need this. So we change the evidence type from still needed to no longer needed for the compiler. Okay, so now that I talked about that, let's refine this model that I did earlier, this decision tree, and talk about, you know, this small refinement of, okay, do I need to distinguish between copy versus move? Then I need this, but don't think about that. Actually, forget about this. I just talk about it for completeness sake, because otherwise the model would not, it would be lying. This model would not be the full truth. So I want to, you know, put it there. But when you design the API, as I said, in my experience, you rarely ever need to think about distinguishing these two things. And if you do, that's great. Then you absolutely already know. You've already probably spent hours and hours on understanding why this is necessary. You've probably done a lot of measurements, performance measurements, right? Because we always measure before we optimize something. So you probably have very good reasons to be thinking about this. So once again, here we have the three intents: owning intent, mutating intent, and the observing intent, which are the three main categories that I want you guys to think about, because this is all that matters. Now, I talked about intent, and I talked about canonical shapes of intent. So we had T, we had Tref and Tconstref as the canonical shapes, but there are actually some other shapes that this intent can take. For example, the observe intent, there is types that look like T, like a value type, but they are fundamentally or conceptually, they are actually observing types. So a string view is something where I observe a string. It gives me like bounds checking and all kinds of things, but it's fundamentally at the conceptual level, it's still very much an observing type. And then also I have std span. I can look at buffers, at continuous buffers of data. Let's say we have like maybe a C API with bytes that are just a pointer, and where I usually do pointer arithmetic, we can use span with, in this case, with a const t, like for example, a std byte or a character or whatever. And it's still observing, even though this is technically, of course, a value type. It just has, it's just a wrapper around some sort of observing type. Same with mutation. Here we have span without the const, so we can also mutate. We can access this contiguous data in memory and do some shenanigans with it. I'm sure there's also other types that I didn't put here, but those were the ones that I really could think about that I use nowadays. And in owning, well, we have T, but we also have something like a unique pointer of T, which in the end is still a T, like the unique pointer itself is the type here. But it's kind of a bit different because it is like a pointer type. And this is also an opportunity to talk about ownership that is encoded in the type. So the unique pointer was just an example. And earlier, if you remember, I talked a little bit about this example way in the beginning, where we have this type that has some sort of task. It has an implementation pointer and so on. And we had this problem here where we don't really know, does any of these functions maybe delete our pointer already? Do we have a problem here? And I said, well, the solution is, of course, shared pointer, right? What does shared pointer mean? Why is it called shared pointer? I don't know. That's also, I'm curious. How many of you have seen something like code that used to look like this, and then later people started doing this? How many people know this type of code? Okay. Well, I thought that would be more, but I've seen so much of it that you can tell probably that I'm a bit agitated. Because people think, okay, great, we have smart pointers now. New and delete is evil. We all know that. We shouldn't use that anymore. Never ever use new and delete. So perfect, shared pointer, and I'm good. I don't need to think about anything anymore. It's amazing. Well, but what did you actually gain? Nothing really, because shared, what do you buy by that? Shared is not just a word. It actually means we share ownership. So in the car metaphor, it's like, okay, I own this car, but also that guy owns the car, and this guy over there, and also Elvis owns the car. And it's like, okay, but whose is it? Who makes the decisions about this? Who decides when to destroy? Elvis does, okay. You do, okay. Okay, in case of doubt, Elvis always decides. So yeah, shared ownership is like, if everybody owns it, then nobody owns it. It doesn't really it doesn't help me to understand any intent. Where should I look for where this is owned? Where is it going out of scope? Well, the person who wrote this code cannot answer this question. Where does it go out of scope? I don't know. Whenever the reference count goes to 0, it goes out of scope. Well, where does it go to 0? Well, I don't know. Nobody knows. The only place, I don't want to hate too much on shared pointer, but I have a bit of a pet peeve with it. The only place where it's really, really useful is in like threaded environments where you pass around things and you run the threads and you cannot actually know which thread is going to finish first. And then it makes a lot of sense because that's the one really good example for shared ownership is threaded environments. Maybe this thread is first, maybe that thread is first, and then who decides when the object should go out of scope? Well, shared pointers are perfect for this. And also something called lifetime extension, where you kind of say, okay, I make a shared pointer from this so that it still lives on, even though the thing that where it was created is already dying. I can always kind of like give it another jolt with a defibrillator or something to like keep it alive. So those are there are some really good examples of using shared pointer, but this is not the one. Okay, so what do we use? Maybe someone can guess. The unique pointer, of course. The unique pointer is amazing because it says, I am unique. There's only one. It's only one owner of this. And if you want to move ownership, if you want to pass this to somebody else, you have to say so. Here we see, okay, we just make a copy from the shared pointer. There's a reference count and so on. Nice. Same thing here. We just dequeued. We don't know what the reference count is. Here it's very clear. I create a task. I enqueue it, and I have to move it. I just have to. There is no other way. If this API here, the enqueue API, takes this thing by value, I have to move into it. Why is that? Because the type of unique pointer deletes the copy constructor. It just says, nope, you cannot copy me, ever. I mean, of course, if you're really brutal, you can probably find a way around it. And there's always ways in C++, but the intent is you have to be willing to give up this object. You have to be willing to relinquish ownership. Otherwise, the compiler will not let you. And this is the power of unique pointers, is that it makes ownership really, really clear. So as you can tell, I love unique pointer. I don't have so much love for shared pointer. All right. So now at this point, I hope that all of you, when they look at APIs tomorrow or whenever you're going to work with some C++, you will look at the API, you will look at the parameters, and you will see intent. You will see intent, or maybe also you will understand that the person who made the API actually didn't think about intent. Might also be an option. But we can now look at signatures and read the intent. Okay, so what does this say? What does this function say? It says, well, I want to observe whatever it is you give me, and maybe, in this case, output it somewhere. But this is definitely an observing intent. Now, what about this? Well, the intent is I want to mutate this object. I want to change it. So once it comes out, it probably has something changed. What about this? Well, I want to own this. Whatever it is, I want to own it. I want to store it. I don't know. Whatever I do with it is my problem, but it's mine. I want this. My precious. And here, well, again, I want to own this. This is probably some sort of polymorphic type, but still, I want to take over ownership. And also here we have an example. All of this applies to return types as well, just kind of the other way around, but we also have the same intent here. You say, okay, I give this to you, you can have it. This is a value, this is yours. Report, in this case, what do I want to do with it? Again, probably I want to just write it somewhere to a screen or something. I just want to observe. I don't want to change this. So reading intent from signatures can really help to become like a better engineer, a better programmer, because, as I said before, code is not really just for the compiler. It's for other humans to understand what you try to achieve. So if there is a bug, they can go through your code and say, okay, this is what they tried. And then it's very obvious what went wrong, maybe. Also, I don't know, anybody here learned Rust, maybe? Okay, couple. So you will also know these terms. They will be very familiar with you, because Rust kind of said, okay, what if we took C++ and thought about these three concepts and made them really part of the language and made the compiler hit you in the face if you violate any of this? Well, yes, that's kind of the advantage of a new modern programming language, is that these intents can be very much encoded into it. Whereas in C++, of course, we have backwards compatibility for, I don't know, 40 years or whatever it is. It's just, we have to rely on people actually following these guidelines. But if you do, you're in a pretty similar, let's say, paradise. I don't know if I've ever used C++ and paradise in one sentence, but it's definitely like a very nice world of milk and honey if you follow these intent guidelines. This is my promise. If you use this, you will live in a land of milk and honey. So what I want you to take away from this is no more rules. I just don't want any more rules, please, for the love of God. We have so many of them. Just a mental model, a simple mental model to think about. So these are the three main things that I talked about today. We have rights. What does the API want? What does it need to do its job? What does it express? Do I want to own this? Do I want to mutate this? Or do I just want to observe it? And then the other end of the equation, the other end of the negotiation, is the types of evidence. Do I still need this? Is it no longer needed? Or did I never actually need it to begin with? And then these things come together as a contract. So the API requests the rights, the call side provides evidence, and the compiler notarizes the contract. I like this metaphor very much. This is what I based my entire talk on, basically, because it just helps me to think when I'm in this situation, what type of parameter should this be? Well, this is what I think about. This is what I've come up with. And yeah, now I'll take the first question, if there are any questions. The microphone.
So we got the time for some questions. Whoever is going to ask the question gets the mic.
Maybe a question. Basically, we in school we code in CP98. How would you go about this intent in CP98 without unique pointers?
I wouldn't.
Thanks.
Well, I mean, that's the thing. In what I showed in the beginning was kind of this pre-C++11 example. And this is exactly the problem. This is also exactly why move semantics was such a big deal, is because there was no real way. You couldn't really enforce any of this. You just had to follow conventions. There were conventions, obviously. There was, if you take a pointer, it depends. Like the name of the function maybe implies something, but you could never really be sure. And this is why there were so many problems with, double free or memory leaks, just because you simply looking at the API, you cannot tell. You don't know, especially if you don't have access to the code. Maybe you just have the header. And, a lot of stuff used to be proprietary as well. The implementations, you just get the headers. What? You hope maybe there's a comment on it, but comments always lie and nobody writes or reads them anyway. And so, yeah, there was no way. And C++11 for the first time made it possible to really encode ownership into the type.
And maybe if I can follow up, is that a standard library limitation or a compiler limitation?
This was very much a language limitation. So a compiler, not the compiler because it's a standard, right? Like the standard just didn't have any mechanics for this. It just didn't exist. the whole R value reference, the double ampersand, was introduced with C++11, and that was the first time we ever even thought about, like, okay, what does it mean to kind of move something? And also the way it's implemented is very much like C++ style, because the move doesn't actually like take it, and then the other object is kind of useless, or the compiler will not disallow using it after moving, just for backwards compatibility reasons, basically. It's like a new type of transfer, like a new type of, we had the copy constructor, now we have the move constructor, but it's very much just a stealing of the data. It's kind of, I hope that answered the question.
What do you think about t-const as a parameter?
That's a very good question. I don't like it. Why? Good. Why don't I like it? Well, because it doesn't really change anything. Okay, let me clarify. T-const, if I put it in the API declaration, the function declaration, it makes 0 sense because it doesn't really change anything. It's just a copy anyway. The only place it does maybe make sense is in the definition, so where I actually implement the function. And I can actually do this. I can put no const in the header, and then I can put a const in the implementation. So if you split implementation headers, which we mostly do, you can have it in the CPP file. In the implementation, you can put the const. But this is very much just for the function body, so that it cannot mutate whatever it gave. But this is more like an annotation almost for myself of like, okay, I really don't want to mutate this value, so I will make it const here. But in the header, it doesn't have any benefit, and I believe there's actually also problems with it, which I can't remember, but I remember seeing something about this. It sort of makes certain things impossible, or it creates problems, actually. So no, don't use const t, at least not in the API, in the declaration.
Well, I feel you, because I also apply a very similar model with one exception.
Yes.
I try to avoid unique pointer like shell pointers,
Okay.
because in the end, what is even easier API is to use just values, pure values. So for instance, in an example, when we have the task, I will never pass a unique pointer for a task. I will pass an object task that cannot be copied.
Mm-hmm.
And then you have to move it around. But for this, you need the use case. Do I care if this object is copyable or movable? So in the intent, you ask yourself, how these objects behaves, and then the signature is changing as well.
Yeah, I agree with you in most cases, but sometimes, we have polymorphic types, so then it becomes a problem. So that's why we still often have to use unique pointer.
I'd like to add to that exactly, because in C++26, which of course is a long way off for people who still are not sure about using C++11, I have to admit, we get indirect and polymorphic, which polymorphic is able to wrap. Basically, you have a polymorphic with a base class, but it can contain a derived class, but it's handled by value.
Okay, I would have to see this.
Yeah.
I think.
So basically, you have a polymorphic of base,
Yeah.
but internally it can be derived, and it will also work correctly. It will call the correct destructors when destructed, but you have a value, you have a copy of it inside. So it's a type erased copy of the actual object, but you only see the base class from the outside.
I really want to take a look at this. I've never heard about this actually. And also one other thing that is cool, in C++26, we finally get optional of reference types, because there's one thing I kind of omitted a little bit. There's some small use cases for still using a raw pointer, which is when you want it to be nullable and mutatable. But I actually never find myself using it ever, I don't know why. I think I just never have the use for it. Maybe because it's nullable is rare, or maybe I don't know. But I mostly use references, and I'm just saying there is probably use case sometimes for raw pointers, but then with optional of references, which should have been there to begin with, I think. With optional of references, we can even get rid of the raw pointers in these cases where we have a nullable. So maybe it's there, maybe it's not there, and sort of a reference type thing. So yeah, also interesting. Any more questions? Well, it's not.
So,
Then thank you very much.
Thank you very much, Fridtjof. Please give him a closing applause for this great lecture.